The morning of March 27, 1944, Staff Sergeant Frank Kowalski stood beside his P-51 Mustang on the hardstand at Royal Air Force Station Leiston, England, watching purple-tinted fuel flow into the wing tanks from a tanker truck marked with unfamiliar warnings. The liquid caught the pale dawn light, shimmering with an almost unnatural iridescence. Behind him, the crew chief of the neighboring Mustang shouted over the sound of idling Merlin engines. "You really gonna run that experimental stuff, Frank? Heard it'll cook your engine in 20 hours. Kowalski didn't turn around. His gloved hand rested on the cool aluminum skin of his aircraft, feeling the subtle vibration as fuel filled the internal tanks. "Wright Patterson says it's cleared for operations," he replied, his voice carrying the flat certainty of a man who had read the technical orders 3 times and still had questions no one could answer. What Kowalski didn't know, what none of the ground crews standing on that fog-shrouded airfield could know, was that the fuel now filling their aircraft represented the culmination of a 3-year race to give Allied fighters a decisive edge, and what the German Luftwaffe pilots would discover in the skies over Berlin in the coming weeks would shatter their understanding of what American aircraft could achieve. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of 150-grade aviation fuel begins not with a single mechanic's illegal modification, but with a realization that swept through Allied air commands in the autumn of 1942. British and American bomber crews were dying at unsustainable rates over occupied Europe. German fighters, particularly the Messerschmitt Bf 109 and Focke-Wulf FW 190, were climbing faster, fighting higher, and outrunning the escort fighters meant to protect the heavy bombers. The mathematics were brutal and undeniable. In October 1943, 9.1% of 8th Air Force bomber sorties that reached their targets failed to return. Another 45.6% came back damaged. These weren't just numbers on a clipboard. Each percentage point represented young men who would never see home again, burned aircraft falling from 25,000 feet, parachutes that never opened, and the persistent, grinding knowledge that German fighters controlled the high-altitude battle space over their own territory. The problem wasn't courage. American and British pilots flew with determination that bordered on recklessness. The problem was physics. German engines, fueled by synthetic gasoline with octane ratings optimized for their fuel injection systems, could sustain higher boost pressures and generate more power at critical altitudes. When a Messerschmitt pilot saw American escorts turning back at the limits of their range, he knew the bombers were vulnerable. The killing would begin. Royal Air Force engineers understood that aviation fuel wasn't simply gasoline. It was a carefully balanced chemical mixture where every component served a purpose. Octane rating measured a fuel's resistance to premature detonation under compression. The higher the octane, the more boost pressure an engine could handle before destructive pre-ignition occurred. Higher boost meant more power. More power meant faster speeds, better climb rates, and the ability to dictate the terms of engagement. In 1942 and 1943, British scientists at petroleum laboratories began testing fuels that pushed beyond the standard 130 grade then in service. They experimented with tetraethyl lead additives, aromatic hydrocarbons, and exotic chemical compounds that existed more in theory than in production refineries. The goal was ambitious. Create a fuel that would allow Merlin and Allison engines to generate 15 to 20% more power without destroying themselves in the process. The breakthrough came in late 1943. Shell Oil and Standard Oil researchers, working in parallel with British counterparts, synthesized a fuel mixture that tested at 150 octane performance number under rich mixture conditions. This meant that under full throttle, with the fuel-air mixture enriched for maximum power, the fuel could sustain manifold pressures that would have destroyed engines running on conventional gasoline. In January 1944, the United States Army Air Force's Materiel Command at Wright-Patterson Air Force Base in Ohio conducted formal trials. 3 aircraft were selected: a Lockheed P-38J Lightning, a Republic P-47D Thunderbolt, and a North American P-51B Mustang. The aircraft were early production models, not specially modified for the tests, This was deliberate. The engineers wanted to know what happened when you simply poured the new fuel into existing aircraft and pushed the throttles forward. The results exceeded expectations by a margin that made cautious engineers suddenly enthusiastic. The P-51B, already a capable fighter, gained 10 to 11 miles per hour in level flight speed. More significantly, its rate of climb increased by 560 to 580 feet per minute beginning at 2,200 feet altitude. At 20,800 feet, where air combat frequently occurred, the improvement remained consistent. These weren't marginal gains. In aerial combat, 10 miles per hour meant the difference between catching an enemy fighter or watching it escape. 500 feet per minute of additional climb rate meant reaching altitude 30 seconds faster on a typical combat climb, arriving at the fight with more energy and better positioning. For pilots who fought in a realm where speed equaled life and hesitation equaled death, these numbers represented transformation. But the tests revealed something else, something that would shape how the fuel was deployed. Engine wear increased dramatically. Spark plugs that normally lasted 30 to 40 flight hours now needed replacement after 12 to 15 hours. Piston, ring wear accelerated. Oil temperatures climbed. The engines were being pushed beyond their design tolerances, trading longevity for power. In peacetime, this would have been unacceptable. In March 1944, with D-Day approaching and the air war reaching its critical phase, it was a trade worth making. The British called it Purple Passion. American ground crews used that name too, though official documentation listed it as Grade 100/150 fuel, or more technically as ANF 44-1 fuel. The purple dye wasn't decorative. It was a safety measure. Purple meant this fuel required specific engine settings, specific maintenance protocols, and pilots who understood they were flying with engines operating at the edge of mechanical limits. By early March 1944, the first shipments arrived in England. 8th Air Force fighter groups received technical orders explaining the fuel's properties, its handling requirements, and the revised manifold pressure limits. Standard operating boost for the Packard V1650 Merlin engine in the P-51 was 61 inches of mercury. With the new fuel, pilots could push to 70, even 72 inches for brief periods during combat. This is where the story becomes human. Technical orders are one thing. Implementation is another. The men who would make this fuel transformation operational weren't chemists or engineers. They were crew chiefs, sergeants in their early 20s, many of them fresh from technical schools in Lincoln, Nebraska, or Biloxi, Mississippi. They had been trained to maintain aircraft, not to fundamentally alter their performance characteristics. In late March and early April 1944, something unusual happened. At the fighter bases, scattered across East Anglia, civilian technical representatives from Pratt & Whitney and Packard arrived, carrying briefcases full of diagrams and speaking in the measured tones of men who had spent months in engine test cells. They gathered the crew chiefs in maintenance hangars and explained something that violated every instinct these young men had developed. They were going to teach them how to make their aircraft faster by intentionally bypassing safety limits. The wastegate, they explained, was a valve that controlled boost pressure by venting excess exhaust gases away from the turbocharger. Factory settings kept boost within safe limits, but those limits, the factory men explained, had been set for peacetime operations and fuel that couldn't handle higher pressures. With purple passion flowing through the fuel lines, those limits were obsolete. Crew Chief Staff Sergeant Harry "Pappy" Gould, working on a P-47 at the time, later described the session. The factory representatives demonstrated how to adjust the wastegate linkage, increasing maximum boost by several inches of mercury. They stressed this was now within acceptable parameters with the new fuel. They didn't call it hot rodding. They called it optimizing for combat conditions, but every crew chief in that hangar understood what they were being told to do. Push the aircraft harder, make them faster. Win the air war. The first combat missions using 150-grade fuel began in late March 1944. Initially, only select squadrons received the fuel. The logistics were complex. Not every refueling station had converted. Not every aircraft had received the necessary technical modifications, and there remained uncertainty about how the fuel would perform under actual combat stress rather than controlled test conditions. Lieutenant William Lyons, a 20-year-old P-51 pilot from Brooklyn with the 357th Squadron, 355th Fighter Group, remembered his first mission on the new fuel. The pre-flight briefing covered the usual details: target, route, formations, radio frequencies. Then, the operations officer added almost casually, "You'll be running Purple Passion today. Your crew chiefs have set your engines accordingly. You'll notice better performance at altitude. Don't get cocky." Don't get cocky. As if the extra speed and climb rate were a minor detail. As if German pilots weren't about to discover that the Mustangs they had learned to respect were now significantly faster and more dangerous. The mission launched at 0800 hours. 51 Mustangs climbing through broken clouds over the English Channel, turning east toward Germany. Lyons remembered the sound of his Merlin engine at full climb power. The deep roar, slightly different with the higher boost pressure. The tachometer read 3,000 RPM. The manifold pressure gauge showed 67 inches. His flight manual, the one published 6 months earlier, listed maximum continuous climb power as 61 inches. He was running 6 inches over the old limit, and the engine sounded perfect. At 24,000 feet, his flight intercepted a formation of Messerschmitt Bf 109s, providing top cover for German bombers attacking Allied positions in France. The engagement developed with the sudden violence typical of high-altitude combat. Enemy aircraft above and behind, American Mustangs pulling up into a climbing turn to meet them. Lyons pushed his throttle to the firewall. 72 inches of boost. The Mustang accelerated in a way that surprised him, even though he had been briefed to expect it. The Messerschmitt he was pursuing, flown by a pilot who understood his aircraft's capabilities, dove away to build speed for a reversal. Standard Luftwaffe tactic. Dive away from the American fighter, use the Bf 109's excellent diving, speed to gain separation, then level out and extend. Except Lyons' Mustang, powered by Purple Passion and pushed beyond its original design limits, didn't fall behind in the dive. He stayed with the German pilot, closed the distance, and at 400 yards, opened fire with 6 50-caliber machine guns. The Messerschmitt twisted right, then left, but the speed advantage that should have saved the German pilot didn't exist anymore. The rules of engagement had changed, and the Luftwaffe didn't know it yet. The burst lasted 3 seconds. Armor-piercing incendiary rounds, the new M8 silver-tipped ammunition that had started flowing to fighter groups in March and April, tore into the Messerschmitt's wing route. Smoke, then fire. The enemy fighter rolled inverted and fell away, trailing flame. Lyons didn't celebrate. He cleared his 6, checked his fuel, and climbed back to altitude. But in his mind, a simple fact had registered. His aircraft was faster than it had been 2 weeks ago. Not slightly faster. Meaningfully, tactically faster. Across the 8th Air Force's fighter groups, similar realizations were occurring. Pilots who had learned to accept certain limitations, certain tactical compromises, suddenly found those constraints loosening. They could catch German fighters that had previously escaped. They could sustain pursuit through maneuvers that used to cost too much energy. They could fight at higher altitudes with better power margins. The Germans noticed. Luftwaffe intelligence officers, studying combat reports and interrogating downed American pilots, began seeing references to improved performance. Messerschmitt and Focke-Wulf pilots reported that American fighters, particularly the P-51s, seemed faster than previous encounters suggested. At first, German analysts assumed this was pilot error or combat stress affecting perception. By mid-April 1944, the pattern was undeniable. American fighters were performing beyond their known specifications. The question was why. German engineers had access to detailed intelligence on Allied aircraft. They knew the P-51's performance envelope with standard fuel. They knew its maximum speed at various altitudes. They had charts, captured documents, and technical assessments based on recovered wreckage. All of that intelligence was suddenly outdated. For the German Air Force, this development came at the worst possible time. The Luftwaffe was already struggling with Allied numerical superiority, pilot attrition, and fuel shortages that limited training hours. Now, the aircraft they faced were faster than anticipated. The comfortable margin that German fighters had enjoyed at high altitude was eroding. Major General Adolf Galland, a Luftwaffe fighter ace and commander, would later reflect on the spring of 1944 as the period when the air war became untenable. It wasn't a single battle or a single defeat. It was the accumulation of disadvantages, each one manageable in isolation, catastrophic in combination, and among those disadvantages, the improved performance of American escort fighters ranked high. Reichsmarschall Hermann Göring, commander of the Luftwaffe, eventually articulated what many German pilots already understood. In a conversation that would become infamous, Göring stated, "When I saw Mustangs over Berlin, I knew the jig was up. The Mustangs over Berlin." That phrase captured the transformation that 150-grade fuel helped enable. American fighters with range to escort bombers to any target in Germany and performance to dominate the airspace when they arrived. For the Luftwaffe, this meant no sanctuary, no safe altitude, no tactical approach that guaranteed survival. But the fuel was only part of the equation. The complete story of the P-51's dominance involved engineering decisions made years earlier, pilot training, refined through bitter experience, and tactical innovations that maximized the aircraft's strengths. The Purple Passion simply unlocked potential that had always existed in the airframe's design. North American aviation's engineers had created the Mustang with exceptional aerodynamics, the laminar flow wing, the efficient radiator cooling system, and the airframe's clean lines all contributed to minimal drag. When powered by the Allison engine, the Mustang had been fast at low altitude but lacked high-altitude performance. The Packard-built Rolls-Royce Merlin with its two-stage supercharger transformed the aircraft into a high-altitude fighter, and 150-grade fuel, arriving at exactly the right moment in the war's timeline, gave it the final edge. By D-Day, June 6, 1944, Purple Passion had become the standard fuel for 8th Air Force fighters. The logistics had been sorted out. Ground crews understood the maintenance requirements, pilots had adapted their tactics to the improved performance, and the Luftwaffe had learned, through the hardest possible school, that American fighters now held both numerical and qualitative advantages. The cost was measured in spark plugs, piston rings, and accelerated engine overhauls. Ground crews worked longer hours replacing components worn by the higher operating temperatures and pressures, but in the calculation of total war, where bomber crews died if fighters couldn't protect them, where D-Day's success depended on air supremacy, these maintenance burdens seemed minor. Staff Sergeant Frank Kowalski, the crew chief who had watched purple fuel flow into his Mustang, that March morning, kept a notebook through the spring and summer of 1944. In it, he recorded engine hours, maintenance actions, and pilot reports. One entry from early May read simply, "Engine change at 118 hours. Pilot reports aircraft faster than any ship in the squadron." Worth it. Worth it. 2 words that captured the calculation. Everyone from crew chiefs to commanders was making was trade engine longevity for combat effectiveness, accept higher maintenance burdens for tactical advantage, push the aircraft beyond peacetime limits, because the war demanded it. The German response to this development was limited by resources they didn't have. They could have developed higher octane fuels. They had the chemistry knowledge, but by 1944, Germany's synthetic fuel plants were under constant bombing attack. Petroleum supplies were constrained. The industrial capacity needed to produce specialty fuels at scale didn't exist, even if German engineers had created their own 150-grade equivalent. They couldn't have manufactured it in sufficient quantities to make a strategic difference. This was the cruel arithmetic of the air war. The side with greater industrial capacity could afford to take risks. They could develop exotic fuels, accept shorter engine lives, and maintain the logistics to support widespread deployment. Germany, fighting a multi-front war with shrinking resources, couldn't match this approach. By late spring 1944, the transformation was complete. The P-51 Mustang, powered by Purple Passion and flown by increasingly experienced pilots, had become the dominant fighter in European skies, not because of a single innovation or one mechanic's illegal modification, but because multiple advantages, technical and tactical, had converged at the critical moment. The transformation in combat effectiveness wasn't abstract. It lived in specific moments, specific engagements, where the new fuel's performance gains changed outcomes that would have been different weeks earlier. April 24th, 1944, Captain John Godfrey of the 4th Fighter Group led his flight through scattered clouds at 28,000 feet over Brunswick, Germany. Below, a formation of Boeing B-17 flying fortresses droned toward their target, vulnerable despite their defensive armament. German fighters were forming up to attack, climbing from airfields that Allied intelligence had identified but couldn't yet neutralize. Godfrey saw them first. Focke-Wulf FW-190As, heavily armed variants designed specifically for bomber destruction. These aircraft carried 30mm cannons and 20mm guns that could shred a B-17 with a single pass. They also carried extra armor and ammunition, weight that made them less maneuverable but devastatingly effective against the big bombers. The German formation was well organized, climbing in a defensive finger-four pattern that allowed mutual support. Their commander understood that American escorts would intercept, so he positioned his fighters to force the P-51s into turning fights that would delay their intervention, while other German units attacked the bombers. Standard Luftwaffe tactics from a playbook that had worked for months, except the P-51s diving to intercept were running on Purple Passion, and the equations had changed. Godfrey pushed his throttle forward. 70 inches of boost, his Mustang accelerated in the dive, reaching speeds that allowed him to close the distance faster than the German leader anticipated. The Focke-Wulf formation leader saw the Americans coming, calculated their approach angle and closure rate based on known P-51 performance, and made his tactical decision. He would accept combat, delay the escorts, and allow the bomber destroyers to reach the B-17s. But Godfrey's Mustang was covering ground faster than the German pilot expected. The intercept geometry that should have given the Luftwaffe fighters time to maneuver and respond collapsed. Godfrey's flight arrived with more energy, higher speeds, and better positioning than the German leader's mental calculations had predicted. The engagement lasted 11 minutes. In that time, Godfrey's flight shot down 4 Focke-Wulfs and damaged 3 others. More importantly, they prevented the German formation from reaching the bombers. The B-17s continued to their target, dropped their bombs, and turned for home. Losses that day were minimal. The Purple Passion running through the Mustang's fuel systems had translated directly into bombers and their crews surviving. These tactical victories accumulated through April and May 1944. Each engagement, where American fighters performed beyond German expectations, reinforced a psychological shift. Luftwaffe pilots, already facing numerical disadvantages and limited fuel for training, now confronted opponents whose aircraft capabilities exceeded intelligence assessments. Oberst Johannes Mackie Steinhoff, a Luftwaffe fighter ace who flew Messerschmitt Bf-109s on the Western Front, later described the period. He spoke of German pilots returning from missions with reports that seemed exaggerated. American Mustangs climbing faster than they should, maintaining pursuit through maneuvers that should have created separation, catching German fighters in straight-line chases where the Luftwaffe aircraft should have had the advantage. Initially, Steinhoff attributed these reports to combat stress or pilot inexperience, but the reports kept coming from experienced pilots, men whose judgment he trusted. Something had changed with the American fighters, and German technical intelligence couldn't explain what. The explanation was actually simple. The Americans had developed better fuel, deployed it efficiently, and accepted the maintenance costs. But from the Luftwaffe's perspective, fighting an enemy whose capabilities kept improving while their own circumstances deteriorated, the source of the advantage mattered less than its effects. By late May 1944, Luftwaffe fighter units were operating under impossible constraints. Fuel shortages, limited training flights, experienced pilots were being killed faster than replacements could be trained. Allied bombing had damaged aircraft factories. And now, the enemy's fighters were faster and more effective than intelligence had predicted. Major Gunther Roll, another high-scoring German ace, participated in a commanders' meeting in early June, where Luftwaffe leadership discussed the deteriorating situation. The conversation focused on numbers, tactics, and resource allocation, but underlying every discussion was a recognition that the air war had tilted irreversibly against Germany. Roll later recalled a moment of dark humor during that meeting. Someone suggested that perhaps the Americans had secretly replaced all their P-51s with a new, faster variant. Another officer replied that it didn't matter whether it was new aircraft or new fuel or better pilots. The result was the same. The Luftwaffe could no longer control the skies over Germany. The strategic implications extended beyond individual dogfights. Air superiority, or its absence, determined what was possible on the ground. The June 6th D-Day invasion of Normandy succeeded partly because Allied fighters had established control over the landing beaches. When Allied troops stormed ashore, German aircraft were conspicuously absent. The Luftwaffe had thousands of aircraft. They had capable pilots and well-designed fighters, but they couldn't challenge Allied air superiority without suffering unacceptable losses. And among the many factors that created that superiority, the improved performance of American fighters, enabled by 150-grade fuel, played a significant role. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Back in England, ground crews measured the fuel's impact in different terms. Staff Sergeant William Schooneman, crew chief for Major Clarence Bud Anderson's P-51 Old Crow, kept detailed maintenance logs. His notes from June and July 1944 show the pattern. Engine changes every 100 to 130 hours instead of the peacetime standard of 200 hours. Spark plug replacements every 12 to 15 hours of flight time. Increased oil consumption requiring more frequent changes. But Schooneman also recorded mission results. His pilot, Anderson, was accumulating victories at a rate that correlated with the fuel improvement. The aircraft Schooneman maintained returned from missions having caught enemy fighters that would have escaped months earlier. The mathematics of maintenance burden versus combat effectiveness favored the aggressive approach. Other crew chiefs made similar calculations. Sergeant Ray Morrison, working with another 357th Fighter Group Mustang, described the spring of 1944 as a period when ground crews understood they were part of something larger than aircraft maintenance. They were enabling tactical advantages that saved bomber crews and contributed to air supremacy. The work was exhausting. Fighter groups operated continuously through the spring and summer. Ground crews worked 12-hour shifts, sometimes longer when aircraft needed repairs before dawn missions. The high-octane fuel increased maintenance demands precisely when operational tempo was highest. Yet the morale among ground crews remained strong. They could see the results. Missions that succeeded, bombers that returned, pilots who survived. These tangible outcomes justified the extra work and longer hours. The purple passion fuel also created unexpected complications. The higher operating temperatures and pressures revealed weaknesses in engine components that had been adequate under normal conditions. Oil seals that had been reliable began leaking. Gaskets failed more frequently. Bearing wear accelerated. North American aviation and Packard engineers worked to address these issues, developing improved parts and revised maintenance procedures. But there was inherent tension between pushing engines beyond their design limits and maintaining reliability. The compromise was systematic monitoring and aggressive component replacement before failures occurred. Pilots learned to adapt their flying techniques to the improved performance. Lieutenant Urban Drew of the 361st Fighter Group discovered that with the extra power available, he could pursue German jets, the new Messerschmitt Me 262s that were appearing in small numbers. The jets were faster in level flight, but they were vulnerable during takeoff and landing. On October 7, 1944, Drew shot down two Me-262s during their takeoff roll. He later described how the improved acceleration from the purple passion fuel allowed him to close distance quickly during the critical moments when the jets were airborne but not yet at combat speed. Without that extra performance, the jets would have escaped. The psychological impact on German pilots was cumulative. Each engagement where American fighters performed better than expected reinforced a sense of declining advantage. Luftwaffe pilots who had once enjoyed qualitative superiority now fought with numerical and qualitative disadvantages simultaneously. Unteroffizier Heinz Knoke, a German fighter pilot who flew throughout the war, wrote in his diary about the changing nature of aerial combat. In 1944, he described missions where German fighters would climb to intercept bombers, only to find American escorts already positioned at altitude with energy advantage. Missions where German formations were bounced from above by Mustangs that seemed faster than they should be. Knoke survived the war, but many of his squadron mates didn't. The spring and summer of 1944 saw devastating attrition among Luftwaffe fighter units. Experienced pilots who had survived years of combat were killed in engagements where they no longer held tactical advantages. By August 1944, the pattern was clear. Allied fighters controlled German airspace. Bomber formations flew to targets deep in Germany with acceptable losses. The Luftwaffe could still mount local challenges, but sustained resistance was impossible. The fuel that made this possible remained expensive and logistically complex. Each gallon of 150 grade required precise chemical formulation using components that were themselves expensive to produce. The tetraethyl lead additives that provided the high-octane rating were toxic and required careful handling. The aromatic hydrocarbons that supplemented the base fuel came from specialized refining processes. American industrial capacity made large-scale production possible. By mid-1944, refineries across the United States and Caribbean were producing the specialized fuel in quantities sufficient to supply the 8th Air Force's fighter groups. British refineries, working from American formulas, supplemented the supply. The logistics of moving this fuel from refineries to operational airfields involved tanker ships crossing the Atlantic, storage facilities in England, and truck convoys delivering to individual bases. The 8th Air Force consumed approximately 53 million imperial gallons of 150-grade fuel between May 1944 and April 1945. That volume represented enormous industrial effort. Chemical plants producing additives, refineries processing crude oil into specialized aviation fuel, ships transporting the fuel across submarine-threatened waters, trucks delivering it to airfields, ground crews pumping it into aircraft, all so that pilots could push throttles forward and gain the extra performance that made tactical difference. The Germans knew about 150-grade fuel by mid-1944. Intelligence reports described its properties and effects, but knowing about a technology and being able to replicate it at scale were different challenges. Germany's fuel situation was desperate by this point. Synthetic fuel plants were under constant bombing attack. Natural petroleum sources were limited and controlled by the Soviets in the East. Even if German chemists had produced an equivalent high-octane fuel, they lacked the refining capacity and distribution infrastructure to deploy it widely. The Luftwaffe was already rationing training fuel, limiting new pilots to far fewer flight hours than their Allied counterparts. Adding a new, more expensive fuel to the logistics chain was impossible. This asymmetry, where one side could afford to develop and deploy advanced technologies while the other couldn't, characterized much of the war's final year. The Allied advantages in industrial production, resource access, and technological development compounded over time, creating gaps that tactics alone couldn't bridge. The P-51's dominance with purple passion fuel became so pronounced that post-war analysts identified the spring of 1944 as the turning point in the air war over Europe. Before that period, the outcome was in doubt. German fighters remained dangerous and bomber losses were significant. After that period, Allied air supremacy was effectively established. Multiple factors contributed to this shift: improved tactics under General James Doolittle's leadership, allowing fighters to hunt aggressively rather than staying close to bombers; numerical superiority, as American production outpaced German losses; better pilot training systems that rotated experienced pilots home to teach new ones rather than flying them until they were killed. But the fuel improvement, arriving at a critical moment, amplified all these other advantages. It made aggressive tactics more effective because fighters could pursue more successfully. It maximized the value of numerical superiority because each aircraft was more capable. It rewarded better pilot training because skilled pilots could exploit the enhanced performance. The P-51H variant, which entered production in early 1945, represented the ultimate expression of the Mustang's design optimized for high-octane fuel. This variant achieved 487 miles per hour at 25,000 feet, making it the fastest production Mustang of the war. Though it arrived too late to see significant combat in Europe, it demonstrated what the basic airframe could achieve when designed from the start to use 150-grade fuel. For the mechanics who had pumped purple fuel into Mustang tanks that March morning in 1944, the war's end brought mixed feelings: pride in the work they had done, relief that the killing had stopped, and perhaps some reflection on how technological advantages deployed at scale had helped determine the outcome. Staff Sergeant Frank Kowalski returned to the United States in late 1945. He brought with him a notebook full of maintenance logs, photographs of the aircraft he had serviced, and memories of dawn launches when purple fuel caught the light and shimmered in the wings of Mustangs climbing toward Germany. Years later, he would occasionally speak about his wartime service. He talked about the long hours and the constant pressure, the satisfaction of keeping aircraft flying despite challenging conditions, and the knowledge that the work mattered, that maintenance actions on a fog-shrouded airfield in England had contributed to missions that succeeded and pilots who survived. He rarely mentioned the fuel specifically. To him, it was simply one more component in a complex system where every part had to work correctly for the whole to succeed. But when asked directly about the difference between standard and high-octane fuel, he would smile slightly and say, "Made the planes faster, made the pilots happier, made my job harder. Worth it, worth it." That phrase recurs in accounts from crew chiefs, pilots, and commanders. The calculation that trading increased. Maintenance burdens for combat effectiveness made sense. That accepting shorter engine lives to gain tactical advantage was justified. That pushing technology beyond its design limits served the larger goal of winning the war. The German pilots who survived to see the war's end carried different memories. They remembered the spring and summer of 1944 as the period when the air war became hopeless, when American fighters seemed to be everywhere, flying faster and higher than intelligence predicted, when the tactical advantages that German pilots had learned to rely on disappeared. Oberst Johannes Steinhoff, the Luftwaffe ace, who had questioned the reports of improved American performance, wrote after the war about the psychological impact of fighting an enemy whose capabilities kept improving. He described it as a grinding awareness that every engagement would be more difficult than the last, that the resource constraints and technological gaps would continue widening until resistance became impossible. For the bomber crews who flew deep into Germany under the protection of Mustang escorts running Purple Passion, the fuel's impact was both immediate and invisible. They didn't know the technical details. They didn't understand octane ratings or manifold pressure. They knew that P-51s arrived when needed, fought off German interceptors, and stayed with the bombers all the way to the target and back. That protection translated directly into survival rates. The loss percentages that had been catastrophic in late 1943 dropped steadily through the spring and summer of 1944. By the time of the Normandy invasion, bomber crews had a reasonable expectation of completing their tour of 30 missions and going home. 6 months earlier, that expectation had been much less certain. The fuel itself became less critical as the war progressed. By late 1944, the Luftwaffe's fighter force was so depleted that Allied bombers sometimes flew missions without encountering significant resistance. The fuel's greatest impact had been during the critical period from March through July 1944, when the air superiority battle was still being contested. In that period, every advantage mattered. The extra speed, the improved climb rate, the ability to catch German fighters that would have escaped, all these factors contributed to establishing the air dominance that made D-Day possible and sustained the strategic bombing campaign that crippled German industry. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The story of 150 grade fuel and the P-51 Mustang is ultimately a story about margins, small advantages, deployed systematically at scale, creating cumulative effects that shaped strategic outcomes: 10 miles per hour of extra speed, 500 feet per minute of additional climb. Rate. These numbers seem modest in isolation, but repeated across thousands of sorties, hundreds of engagements, and millions of gallons of specialized fuel, they help determine who controlled the skies over Europe in 1944. For Staff Sergeant Kowalski and the thousands of other ground crews who serviced those aircraft, the technical details mattered less than the mission results. They pumped purple fuel, changed spark plugs every 12 hours, and worked through exhaustion, because the work served a purpose larger than themselves. For the pilots who flew those missions, the improved performance translated into survival and victory. They pushed throttles forward, felt the extra acceleration, and knew their aircraft could do things that would have been impossible months earlier. For the German pilots who faced those Mustangs, the fuel represented one more disadvantage. In a war where disadvantages were accumulating faster than they could be addressed, they fought with courage and skill, but courage and skill couldn't overcome the combined weight of numerical inferiority, resource constraints, and technological gaps. The war ended. The purple passion fuel became a historical footnote. Most of the Mustangs were scrapped or sold as surplus. The ground crews returned to civilian life. The pilots who survived carried memories of missions flown and friends lost. But for a critical period in the spring and summer of 1944, the combination of an exceptional airframe, a powerful engine, and fuel that pushed both beyond their design limits created an aircraft that established air superiority over Europe, not through a single innovation or one dramatic breakthrough, but through the systematic application of multiple advantages that, taken together, became overwhelming. The mechanics never called it a miracle. They called it maintenance. The pilots never claimed it won the war alone. They knew air superiority required coordination across bomber groups, fighter groups, intelligence services, and ground support. The German pilots who faced them understood that no single factor determined the outcome. It was the accumulation, the relentless pressure from an enemy with more resources, better logistics, and technological advantages at every level. 150 grade fuel. Purple Passion, ANF 44-1. By any name, it represented a commitment to gaining every possible advantage, accepting the costs, and deploying improvements at the scale necessary to make strategic difference. That commitment, multiplied across thousands of aircraft and millions of gallons, helped establish the air superiority that made Allied victory possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.